Hello, welcome to all of my combo lords out there. To anybody who was joining me live, my apologies for the little delay. Had to end up restarting my computer and things were working better after that. I think I need to clear space on here or something or another. As you may know, I am not a tech wizard. Hopefully, by a grade or two from now, I'll have somebody else running the tech part of the streams. We'll see when we can get there, but for now, we are all going correctly. And the reason for today's stream is, well, I was considering streaming anyway, but when I was pondering what topic we would be discussing, I played a little game I like to do some mornings, which is look up which strange holidays supposedly occur today, such as those National Day of Whatever or International Day of Whatevers, all of those little holidays. And it might seem like I wouldn't be somebody who might celebrate as many holidays because I mock the calendar system a lot. One of my recent episodes was about how our calendar system is full of flaws, and hopefully before long we will update to some other way of keeping track of our days within the months, fix some things like the discrepancy between this month's amount of days and other months' amount of days. But while we are stuck in our calendar system, we couldn't still appreciate the holidays, and maybe even more of a reason to do so, because in combo class we have a theme of thinking of unconventional ways of doing currently accepted structures, like counting in another base, or changing the alphabet, or changing the calendar. But although one of our goals in combo class is to spread awareness of these things being flawed and being open to possible changes. Another thing in combo class is appreciating whatever we have around us to whatever degree we can. So while we are stuck in base 10, we might as well enjoy our digit tricks that things like 9 can do. And while we're stuck in whatever alphabet you use, you might as well appreciate things like rhymes and alliteration. And if we're stuck in this calendar system, might as well look at some silly holidays that have been named for today. Now, sometimes the holidays do range to, maybe I shouldn't call all of them silly, some of them have historical reasons and stuff, but some of them definitely can fit in the silly category, which doesn't necessarily mean a diss. It is just a trait about a thing, doesn't necessarily mean it's better or worse from being silly. So, what we're going to have to do is look at a few of today's holidays, and I'll mention two of them that stood out to me. So let me shrink myself a little bit. And when I shrink here, well, now I'm gone. Now I'm just going to shrink. We can see that some of the days that today is claimed to be, we'll get to that first one last, include things like some awareness days that are, good to keep your mind on, as well as some that are a little more random, like Rose Day or Wave All Your Fingers at Your Neighbor's Day. And of the ones that are, debatable how random they are, two that seem like good chatting topics are National Periodic Table Day, because periodic tables are very interesting and might as well take a peek at some of the elements. And the other one that's right up my alley is E-Day. E is a classic mathematical number. This isn't celebrating the letter E, it's celebrating the number. And like many simply named math numbers that get a day, like Pi Day, it's a little confusing. Pi Day can also mean Eating Pie Day, which is a different day, is called PIE Day, than is the one called PI Day. And E-Day could mean all sorts of stuff. But here we're going to assume, as it was named for, that the E we're talking about today is this classic irrational number that I believe is a little underrated because although it gets a lot of credit in the mathematical community, the number pi, which has similarities to E, gets a lot of credit in our society. And a lot of the cool traits that pi has, E also has. They're in the same category of number, of a transcendental irrational number. And they both show up all sorts of places. The difference is that E shows up in a crazy variety of mathematical places, often related to rates of growth, but also related to all sorts of things. And pi usually can be boiled down to a circle being involved or something circular. So it's hard to pick a favorite. I don't know if I could personally pick a favorite between something that represents circles that are all over. Circles are everywhere in circular motion. It's part of dimensionality. So it's hard to pick a favorite between that and E, which shows up so many cool places in math. A stunning amount of places, and sometimes more surprising places than pi. And that's why I think it's underrated, because pi gets a lot of credit in our society, and I think E should be known by more non-mathematicians. Now, funny enough, when we look at what they say for E Day on here, one thing they note is how to observe E Day. And they give a little explanation about it first. And part of the explanation is how one place it shows up is when calculating compound interest, which is true. I've made a short that is about how one of the simplest ways to explain E is in terms of bank interest. However, I don't know if I agree with how to observe E-Day is to put money in a savings account where E will be used in part of the formula somewhere of how much interest you end up getting. Come on. There's enough holidays about money. We can't have a holiday just to study the number E, to try and learn some new facts about it. So, today, I'm not saying this is the goal. If you want, you can put some money in a savings account, sure. But today's goal is going to be to celebrate and learn about the number E. And I have a lot of facts I want to share with you guys, some of which will be things that have shown up in shorts or live streams, and many of which I haven't had the chance to mention because E shows up all over. We will see it algebraically. We will also see it on Desmos. We will be pulling open Desmos later, and today, instead of focusing on what wacky combinations of trig functions can create crazy shapes, we're going to focus on a graph or two that has E involved. And those trig ones are more likely to have pi or multiples of that involved. But there are many graphs that have E involved. Now, let's, before I look at the comments, make one more note, which is that when should E-Day have been? E is approximately 2.718 so and so on. And so it's often celebrated on the 7th day of the second month. Right away, you get a discrepancy between people in places like me, where you put the month first, where this is how I would write that date because of where I live, and places that put the day first, because there are places that would call this 7-2. And so they would want to celebrate E-Day possibly on the 2nd day of the 7th month. So there's already a little discrepancy there. But I think there's an even more fun way we could approach when E-Day should land. Now, I'm going to be using the system of months where I am living in, not saying I agree with that. I can definitely see the logic behind people thinking that it should go day then month. But where I live, it is written like this. And I think if we're going with that, stuck in the calendar system, stuck in it being written this way, that it would be more fun to take our approximation further. It's closer to 2.72 if I round that 1/8 than it is to 2.7. So what if we celebrated it on the 72nd day of February? You might say February doesn't have 72 days. Well, why don't we just roll over? Why don't we say the 72nd day of February is the 72nd day from February 1st being the first day? That would land it somewhere in April, and on a different day when it was leap year or non-leap year. But that would be more fun. So I think we will do an even more E-based extravaganza, maybe on my main channel, on the other E day, the 72nd day of February. On a similar way of rolling around that I thought could be funny here, we could think we could roll around on well, no, I'll do those in a second. We could think we could roll around on also Pi Day, which is 3.14159, etc. Hey, squirrel. But if we do that, which could work, we could say that pi is going to be 3.141, or if it's 3.142 would be the closest approximation of those. So why wouldn't we celebrate Pi Day on the 142nd day of March, using a similar rollover technique, where if March 1st is the first day, it's the 142nd day from then. That'd be more fun, maybe. Could also celebrate their days based on other numbers that have to do with approximations of them as opposed to decimals, because decimals are just one approximation. Like pi is also close to 22/7, so we could also celebrate it on July 22nd, Pi Day. And one more thought about that rollover idea. Another way we could think of rolling over is, I realized one day, maybe 7:06 is the spookiest time, or the most cursed time. At least for people who don't like the number 666, because 666 would be 7:06. So if we roll over, you know, anyone scared of 666, watch out for 7:06. All right, so that's some thoughts about when maybe we could celebrate E-Day, but most people are calling it today, according to these things, so we're gonna do a little E-celebration today. Let me take a little peek at the comments, and then I'll run you through my version of what they're describing about its relationship to compound interest, and then we'll find some more crazy stuff about it. So, let me make myself large again. I'll use a whiteboard for this bit. And also when I'm large, I can just check the comments on here without it clogging everything up, because there ends up being a little delay. And howdy to everybody joining me. Glad to have you all here. And yep, there's many ways to possibly put these days. And feel free to leave your own favorite facts about E if you have any, like how someone here is mentioning that the area under a particular curve is E. And someone's wondering why orange juice sometimes tastes bitter. And although that is a random question for me to jump to, I may have the answer. I think it often tastes bitter when you have toothpaste in your mouth or something minty. And I don't know the scientific reason for that phenomena, but if you brushed your teeth and then had orange juice, I think that is something that occurs. Now, if that's not the case, then maybe they just used some really underripe oranges when they made it. And someone's mentioning another spot E appears, is that 1 under E occurs when you're trying to optimize certain application processes. Now, 1 over E will show up some places here too, because numbers reciprocals, when you divide 1 by them, are very important. They show up all sorts of cool places, so if we're looking for a number to show up and its reciprocal shows up, that definitely counts. Now, to start off on what is E, which I have made a short about this, but it'll be just a couple minutes of the stream too for a little refresher. One way we can calculate E is, and which whiteboard should I use? This one got dirty, but it works. So, I'm sitting on the remains of my desk, by the way. We will be getting a new desk for grade -2, so Might as well milk the last use out of this one I can. So the number E, which is approximately, E is approximately 2.718. One place that it shows up that's pretty easy for people to digest is that if we have a bank that gives us really good interest, in fact, they give us 100% interest. Now, this is going to make E show up on its own in the answer, but of course, E, like, we could find E in other formulas, even when it's not this simple of an analogy. But this is going to be to make E show in an extra clear way. We're going to say we have this really good bank that gives you 100% interest. That means for the amount of money you have in there, they give you that much money back every time they calculate the interest. So if we put $1 into the bank, then we start at $1. And if they just at the end of a year do that interest thing once, they calculate on the dollar, they're like, okay, you had $1, we give you 100% of that, you get $2 total. But, oh, and one of my cats is visiting. Hey, Sage. Who's a good little Sage? There's a good little Sage over there. Hi, Sage. And if we calculated the interest more often, if the bank was even better, and they said, we give you not only this 100%, but we're going to check halfway through the year and do it twice during the year. Well, halfway through the year, they see your $1 and they give you 50 cents because they've calculated half a year's worth of what you currently have. And so you're up to 150. Then when they give you the other half of the year at the end, you're getting 50% of 150. You end up with 225. And what if they calculate it more and more often? If they keep compounding it down to like the millisecond, you end up with E dollars as what you approach as you compound more and more frequently. E dollars at the end of the year, if they keep doing that more and more often. And this relates to one of the ways we can write E, which is that it's the limit as n goes to infinity of 1 plus 1 over n all to the power of n. Now, some people at first think this would be wrong because they think that, well, as we zoom toward n being a massive number, this part seems to go toward 0, meaning the inside parentheses seems to approach just 1, and that part's something massive, and 1 to the power of something massive is still just 1. So some people assume this would just be 1. But you can't just crunch both of these to infinity and see what happens. We have to see the rate that happens as they're both going up. And now let's see on Wolfram Alpha how quickly it approximates it. If we see, like, if we try and jump to 0 there, like some people think you could try and do to find the limit, then we're basically trying to be like 1 plus 0 to the power of something nearly infinity. And of course that's just going to be 1. But we can't just crunch them that way. We have to see what they approach as the pair of them evolves. Because n is always the same in that denominator as in that exponent. So let's test it at different values. If we say 1 and 100th, all to the power of 100, then 2.704. That's kind of close to E. If I add a few more zeros on there, we are really close to E. And no matter how many zeros I tack on there, as long as I'm putting the same number in that denominator and that numerator, then I'm going to get approaching E. So it doesn't crunch down to 1 like some might think. It steadies out and gets closer and closer to e. So this is one of the most common ways of defining e, although there's a way I like even more. But first let me share a way I like less, which is sometimes people try and get out of having to explain what e is by using this little circular explanation. Sometimes people will say, e is the base of the natural logarithm, which is, the natural logarithm is written ln of some number, and it means how many times does e have to go to some power to be that number. We also could write it log, sometimes with little e down there and a thing, and in certain fields they'll just write it as log and assume you're meaning e down there, but in other fields, if you write log, they assume it's a 10 down there or a 2 down there. So, good to clarify, this ln ended up being a way they write the natural log. But then, sometimes the same people who say, oh, what is e? E is the base of the natural logarithm, meaning that ln, e is the number that log of its base has this nickname. Some of the people then describe, what's the natural log? Oh, the natural log is log with e at the base. And it's like, come on. You can't just say, what is e? It's the base of the natural log. What's the natural log? It's the logarithm that uses e. That is such a simple little circular loop that it doesn't give you any data. So there are ways we could define the natural log by having another way of saying this is the definition of the natural log, thus its base is the number e. Or you can go, here's the definition for e, the natural log is the one that uses that. But you can't have both. You can't take your cake and eat it too. You gotta define at least one of them. So that's something that's bugged me about occasionally seeing those definitions, is I'm like, you didn't actually describe it. So one way I like more, though, that is a better way to define it, maybe not better than this way. This way is pretty elegant as well, but I especially like, because it relates to two concepts I like, is something related to factorials and related to infinite series of reciprocal numbers. Reciprocals being that inverse, 1 divided by something, and an infinite series being when you add up an infinite amount of a thing. And the reason why I haven't gone into this too much, although I think I may have mentioned this on a stream once, the reason I haven't dived too deep into this is because this will definitely show up within one of the next episodes in grade -1. Maybe not the very next episode, but one of the remaining grade -1 episodes is going to be about adding up infinite series of numbers, such as reciprocals, and which ones converge or diverge, meaning something like 1 plus a half plus a fourth plus an eighth plus a 16th and stuff just approaches a steady number, whereas other things fly off to infinity if you keep adding them. Well, it turns out that this is one that I'm going to show you now because it relates to E, and don't worry if this is a mild spoiler from that episode, because that episode is going to have so many different reciprocal series examples that this is just one of countless cool ways that series can converge on things. Plus, in that episode, I'll show you an even more fun way that you could calculate it by hand. But just to give a little preview, because it's one of my favorite definitions of E, is what happens if I take the reciprocals of the factorials up to some point and add them up? Well, we're gonna start with 0 factorial, and I've made a short and an episode on my main channel that mentioned that 0 factorial does equal 1. So we're not going to get into that here. If anyone doesn't know that, like, logic behind that equaling 1 yet, watch the episode on my main channel about factorials. Also, everyone should make sure they've watched the newest episode on my main channel about pan-digital numbers. And we're going to start with 0 factorial, which is 1. What happens if we add up the reciprocals of the factorials? So if I'm going up for a little while, what I basically have is, we can type this in Wolfram Alpha now. We basically have 1/1 plus another 1/1, because 0 factorial and 1 factorial got us that. And, ooh, they already know it's 2. But that's not where we're stopping. Plus 1/2, we're now at good old 5/2. Plus a 6th, which is 3 factorial. Plus a 24th. Plus a 120th. And let's go up to maybe 7 factorial. We get, here's 6 factorial, and, no, 720. 6 factorial, and here is 7 factorial. And let's see what the series has approached at that point. Because after that point, we'll note that the factorials are getting so small on the denominators that this is going to be one of the series that doesn't make it to infinity. No matter how many factorials you add on, they get smaller at the type of rate that this will end up converging toward a number that it never passes. And whatever number it gets closer and closer to without ever passing, we can say that the infinite series equals in terms of its limit. And let's see where we're at up till there. What do you know? Really close to E. And, yep, E is the number that no matter how many factorials we tack on here, we will get closer and closer to, but never pass. So one of the other definitions of E, apart from that infinite limit, is a different way of getting about it with infinity, which is, it is the sum of the reciprocals of the factorials. Now, there's even another infinity-based way we can make E, which is its continued fraction. Let's look at what this means. A continued fraction like this, which there's also been an episode about this on the main channel, so another thing that I'll just do a quick refresher on, but there's a whole episode about this for those who want more. Although, yes, I did have to make a clarification in the description of the main channel episode that on this exact continued fraction, I missed one of the digits. I didn't write the 8 or something. So I had to make a mild clarification in the description that when I said something related to all the even numbers here, it was all the even numbers. I missed an 8. Stuff happens once in a while. But here I will make sure to add the 8 to make amends. So I just flip this whiteboard. On this side of it, what that continued fraction means is that if I go 2 plus, all of these numerators are going to be 1 for this type of continued fraction. 1 over 1 plus 2 over 1 plus 1 over 1 plus... Oh, no, wait, no, sorry. 2 doesn't go there. 2 goes here. Plus 1 plus 1. 1 over 1 plus 1 over 4. And, oh, I'm not going to make it to the 8. Sorry, 8. There is an 8 in there somewhere. So, and that 8 also functions as a infinity sign because you're supposed to continue these infinitely. Well, there's a pattern here. The pattern we can see in the continued fraction that they list here. These are the denominators. All the numerators are 1, and the denominators go 2, 1, 1, 4, 1, 1, 6, 1, 1, the next even number, 1, 1, the next even number, 1, 1, and so on forever. And that continued fraction also approaches E, plus all of these wacky things. Look at all these other continued these aren't written how a continued fraction would write them. They're written with an infinite something there, but look at all of these different things that equal E. Look at all of those. All right. So those are a few of the ways in which we could define E, among many ways. Theoretically, any of the weird places E pops up that we'll find today and in future episodes could have been your original definition. But those are some of the best ways to define E. It's awesome repeating simple continued fraction. It's awesome limit form. And it's awesome infinite series of factorial reciprocals form. And a less cool way to do it is to do the cheater way that some teachers do, where they say E is the base of the natural logarithm. What's that? It's the logarithm with E at the base. So if you're a teacher, don't go with that explanation. It's not helping anyone. And someone's also mentioning that we could also define it recursively. We could say that for n factorial, it's always n times n minus 1 factorial. So you can define it in a recursive way like that as well. Another way in which we could define it is related to the function e to the x. E to the x has some very important properties when you look into calculus and you look into derivatives and such. And so another way that is a logical way to define it is on e to the x as a equation, which would actually look quite similar to if I had continued that graph of that really good bank, but I had continued past year 1. Someone's wondering about infinity factorial, and we cannot really call infinity factorial a particular thing. That's sort of a nonsensical statement, because factorials on their own really only work for a positive integer. We've extended it to 0 to a degree because it's a logical extension. And then you can extend them to other things with this thing called the gamma function that I'll make an episode about someday. And the gamma function is a really cool way that you could make an equation that maps something like the factorials, but also in between points and negative points. But theoretically, you could say, try and follow out the gamma function pretty far, but in the positive direction, it gets bigger and bigger. And so you wouldn't really be able to say, if you said what is the gamma function approach as you get to bigger and bigger factorials, or just what do the integer factorials approach, it would be infinity. But you can't just say, what is infinity factorial without clarifying. So that is some interesting stuff there. Let's now look at one or two graphs that are going to have E pop up. And then we'll just scroll through some of Wikipedia's article about it to learn a bunch of fun facts. But we might as well pull open Desmos for a moment. And what we're going to see there is a function or two that might lead to E being involved. So the first of these did show up in one of my shorts already. It was if we ask which number to the power of 1 over itself gives the maximum value, which also means the nth root of n, because the nth root of something is also that number to the power of 1 over n, in terms of the principal root that the radical symbol also means. And if we graph that, well, first, if we don't graph it and we just plug in numbers, 3 is the winner of the whole numbers. The cube root of 3 is bigger than the square root of 2 or the fourth root of 4, or the others. And If we graph it, though, and look for in-between values, y equals x to the power of 1 over x. Well, the maximum here, which is our output of that, if we look, is like around there. In fact, they label it. There's the maximum, that dot. And what do you know? It is e as our x value. E to the power of 1 over e creates our maximum output. 3 just wins the integer awards because it's the closest integer. Now, here's another one that didn't show up in one of my videos yet. What if we asked, so we're going to get rid of this. What if we asked, well, 2 to the power of 4 happens to be equal to 4 to the power of 2. That's kind of neat. Because we could have phrased this last question, the y equals x to the 1 over x, as starting from saying maybe, well, the square root of 2 is the same as the 4th root of 4. So that's interesting. Is the cube root of 3 more or less, or what else, you know? But what if instead of looking for a maximum here, we were looking at, so 2 to the 4th equals 4 to the 2. Are there any other cases that match this type of pattern, which is x to the y equals y to the x? Well, if you're looking for whole numbers, apart from if you allowed 0 to the 0 equals 0 to the 0, which is very debatable whether you'd allow that or not, most would not allow that. And in any case, maybe we could say, let's not, well, we could say that when they're equal, it's very obviously true, you know, like, whatever, pi to the power of pi obviously equals, if we switch those, pi to the power of pi. So let's say they have to be different, and then that'll exclude us needing to worry about whether 0 to the 0 fits or not. So if they're not equal, unfortunately, this is the only solution where both of them are positive integers. But it's not the only solution in general. You could imagine there's a whole family of things that work for these. And in fact, certain things might not work. Like maybe if I say, what if x is 1 and y is not 1? Well, 1 to the power of that is still going to be 1. And then something non-1 to the power of 1 will be non-1. So we could see, one of them can't be 1. But if I make one of them 2, the other one's 4. But what if I try to look for non-whole numbers and I had something set that I want one of them to be? Like, what if I want x to be 3 and I want y to not be 3? Well, we could say I have now 3 to the y equals y cubed. And we could go about trying to find a solution to what might fit that. But a quicker way can be to say, why don't we graph x to the y equals y to the x, and there should be a set of solutions that, first, let's just say, like, this line, y equals x, is just a line. This set of solutions up here should work. These points, like that, and that. Because when both the numbers were the same, it was a trivially true case. But what about 2, 4, and 4, 2 also worked? That means there should be a solution there and a solution there. And if we graph it, we see all of that, all of that is true. And let me make sure you can see this. Okay, yep, we got enough room. we can see all of that is true. We have this line of the positive stretch of y equals x for the trivial solutions. And then we have this other web-like thing that curves up that passes the points 4, 2 and 2, 4, and which can't have any of them be 1. It has an asymptote at x equals 1 and at y equals 1, where those will get closer to but not pass or hit. And so 1 only works when the other one's 1. Otherwise, we're going for the asymptotes there. But if I go above that, other stuff does work. I can find that if I wanted one of my numbers to be 3, the other number would be this number, approximately 2.4 something, 2.48 or something around that would be the answer when one of them is 3. Now, why do we have this open today? Why am I talking about this today? Well, there's one point that's kind of interesting here, which is that this single graph gave us two things that intersect in a spot. There's one spot that's true in two ways for this, because it's true because it's on the trivial line, and it's true because it's on that curvy line. It's that intersection point right there. Hey, Sage. Got another visitor. Well, same visitor as before. A very nice one. And if we look for that intersection point, let's zoom in and see, what do you know? It's E. It's when we put e to the power of e equals e to the power of e. Of course, it's true for the trivial reason. But there are solutions ever so slight to that aren't trivial, things that are really close to e for each of these, because e is also on the curvy line. So that coordinate is EE. It's just funny how many places E shows up. I remember when I was doing my tetration episode. We're going to have to just watch one bit from that because it is just so random. So tetration is this thing where it's the level beyond exponents. Now, a bunch of you have probably already seen that episode. It's the most popular one on my main channel. But I need to pull it open for a second just because it has one of the craziest ways that E just randomly pops up on a graph-like thing like that. Although this isn't showing it on a graph, really. It's showing it more algebraically. If we look at this one, which is for some reason the most popular one on the main channel, then, oh no, make it smaller actually, and let's, because I don't want to block too much of it, let's see where the crazy E part is. So if I'm looking at this stack of 2's, if I keep tetrating it toward infinity, I stack more and more of itself as exponents on itself, it approaches 2. But are there anything I could stack on top of themselves as exponents that wouldn't fly up to infinity, but that would be bigger than 2? There is. It turns out that you can make this stack of a to the a to the a to the a going on toward infinity of the same number a converge to e. Any higher would go toward infinity. But that's not the craziest E type of thing here. Look at this. I'm just going to play this clip.
That any tower like that that's infinitely tall can converge to without diverging up toward infinity. And if you thought it was weird that the number e popped up there, you're not going to believe this. The range of values that we could tetrate infinitely many times and have it be a convergent finite value is when that number is between e to the power of negative e and e to the power of 1 over e.
Isn't that just ridiculous? The maximum is e, and the range that is convergent is e to the power of negative e to e to the power of 1 over e. Which is insane. So, not only does e pop up a lot of places, but weird mutant versions of e pop up all sorts of places. By the way, there's a lot of wild little bird action happening here, and I'm going to take a brief break to show you a cool bird thing, which is the other day I mentioned there was a nest up there and I tried to show it. I'm not sure how well it showed it, but I've been seeing birds actually attending to the nest. I think that they're either like building the nest more or that they already have eggs in there, or baby birds, because there's these birds that keep flying in and out of the nest, like bringing stuff to it. And they're the same ones probably that are giving us the nice songs. And it's, let me see if I can point where it is. It's like up there. You see that nest-like thing? Like right up there. That's where the birds are doing a lot of cool stuff. I'll keep an eye out for that and let you know if I see them doing more cool action over there. In any case, we're getting their nice songs for now. So, let's take a little stroll through just a couple of the many things I'm sure Wikipedia has to say about E, because they're going to have a nice long article about it. Now, E, of course, was, well, maybe not of course, but E was named after the mathematician Euler, E-U-L-E-R. Looks kind of like Euler, but most people pronounce it Euler. And he was one of the greatest, probably the greatest mathematicians of all time, and came up with so many things they named after him. There's even another constant that often is called Euler's constant, or called Euler's number, compared to this one being called, this one's called Euler's number. Another one they often called Euler's constant, although we can give it a longer name and call it its full name. So too much stuff is named after him. He even got a letter as a variable named after him, but he deserves it. He had so much cool stuff. Now, here we have a good one, which is a graph of the equation y equals 1 over x. E is the unique number larger than 1 that makes the shaded area equal to 1. And let me make sure I'm at, no, you're not seeing it yet. Here that is. Look at this. Y equals 1 over x. E is the number where the shaded area is equal to 1. Then, of course, you get this insane classic that I'll explain more detailed in the future. E to the I pi plus 1 equals 0. We got this classic definition. And we got our compound interest definitions. Here we have one about probability theory. As a gambler plays a slot machine that has a probability of 1 in n, and they play it n times, as n increases, the probability that the gambler will lose all n bets approaches 1 over e. We also got derangements, which are kind of similar to factorials, in that factorials represent permutations, which are similar to derangements. And we get some more wacky stuff going on here. Here's this one they noted as well. Our maximum value there occurs. And this one about maximizing a product of the sticks is actually really beautiful. That will come up in a future episode. One place that E shows up, or almost gets the chance to show up, that's related to a degree to this broken stick thing they're mentioning, is this idea called the integer complexity, which I'll go into in a whole episode about on my main channel, and I purposefully haven't mentioned it yet because I want to make sure I get that episode the way I want to. It's a really cool topic. So that's a whole topic that I don't want to mention yet, or it'll spoil something I'm planning that also has E. Here we get more calculus and geometric things. Here we got the fact that E is the number, the unique one, such that the derivative of e to the power of something is that same thing, which can be seen as, in a way, when you look at, if you were looking for a graph that at any point its slope was equal to its value, similar to if you had a car whose velocity was similar to their position, or even similar in a way to a car's acceleration and velocity being similar, E would be involved. And this one right here is an algebraic way of saying that graph one, where they were saying the area between 1 and it summed up from 1 over t, basically. And this is that one about it being its own derivative when you put e to the x, and its own antiderivative. And here we get some wacky other phrasings of some of these identities and other similar identities. Yeah, so there's just so much about E. Here's another way we could have done that continued fraction if we want. And so many places it shows up. So that's cool. Donald Knuth, who's a great guy at thinking about different bases, like I've shown up in some of my episodes, and great thinker about math and computers in general, says that his version numbers of his program just get a new digit of E as they go forward. I'm down. That sounds cool. And yes, due to the emergence, many have paid homage to the number E, which is what we're doing today. So, a lot of good stuff. To anyone who wants to learn more about E, read more through this article. And here they even have a funny one. You know, I said there's too much stuff named after Euler, which isn't his fault. He was too brilliant. They had to name all this stuff, but they might have needed to name it after other people. Here, you see that at the top of the article, all about list of things named after Euler, it says that he discovered so many things that some discoveries and theorems are attributed to the person who proved them second, after him. Otherwise, too much stuff would be named after him. It's like, we already named something Euler's conjecture about squares. We can't name his other things he found about squares that. And here we can see that all of these numbers are sometimes called Euler's number or something very similar. So very confusing. We can't always call E Euler's number and have it be fully clear, because we can see we have many other types of things. We have Euler numbers being different, Eulerian numbers, the physics type of Euler number, the algebraic topology type of Euler number. The two types of different topology fields have different things they call Euler number. And with this one I refer to as Euler characteristic, because that is a good nickname for that one. And you get your lucky numbers of Euler. You get Euler's constant. And you get your, oh man, a lot of numbers have been named after this guy. And like they said, he discovered so many things that some of the numbers he discovered were probably then just named after the person who proved them after him to avoid having too much trouble. So, this guy is a hero, discovered many great things, and quite possibly the greatest mathematician of all time so far. So let me make myself big again and look at the chat for a moment, which I haven't in a while. Thank you all, of course, for joining me here today out in the combo classroom where we were able to dodge the rain today, which is nice. We get a little fresh air. And let's see. Thank you all for your comments. Very awesome to see. Cannot involve all of or answer all of the ones that are asking questions, but I do appreciate them all. And someone's asking whether Euler or Ramanujan is greater. And if you had to say based on their achievements, you'd probably have to say Euler achieved a lot more and discovered a lot more. However, Ramanujan died very young, and so it's debatable whether he had lived a full life, whether he would have been just as brilliant or more. He is equally a personal hero of mine because he had a very unconventional schooling and discovered so many things himself, possibly because of his unconventional schooling, and also just because he was a genius. And so he has some combo class vibes to him. And they are equally my favorite in terms of if I had to pick a favorite out of them. They're both very dear to me. However, I would say Euler probably discovered more things because he got to live a lot longer and just had such an insane amount of work he did. And someone's wondering if any number greater than 5 can be written as the sum of 3 primes. Some questions like that are still open related to Goldbach's conjecture you could look up, which Goldbach's conjecture relates to that. And leave some more comments while I need to run and grab my charger. We just got to low battery and I forgot to bring that, so I'm going to grab that real quick. Feel free to leave your comments. I will, I guess, leave you with the birds as opposed to with the Wikipedia. Maybe something nice will run by the background. I'll be back soon, and leave your thoughts. folks, here we return. We'll need to move the computer. All right, time to see how bad the glare is back here. Now, you guys know how the live streams have a ton of glare and there's not quite as much of it in my episodes. Well, it does actually take a lot of work to avoid that glare in the episodes. So I might need to get some sort of like canopy or something over here, like some big umbrella or something, so that I can, something big to like block out some of the sun. But sometimes you get rainbows and stuff. All right. This should work for the meantime. Although now I need a chair. And this chair doesn't have its back, but it has enough of it. All right, thank you all for sticking around and hanging out in the combo classroom when I need to run on a mission or whatever. And to people wondering about AI, that is a good question, because I do think in a minute, I have that open. You may have seen the tab was already open, if you can see that part of the screen, maybe not. But I did have that open in the background here because I made a short about that yesterday where I collected some of the worst answers that ChatGPT, the AI, has given me. And some people mentioned that it's upgraded its math capabilities at the end of January. Oh, this isn't charging. Let me click this. And so apparently it's updated its capabilities. However, some of the answers I'd gotten from it that were really bad were since then. So not all of the answers that were really bad that I compiled in the short were before the update. So I'm curious on how well this update actually updated. I'm sure maybe they improved some of the things. It did stun me originally that with something that's capable of holding a communication, of talking back and forth with you, that it's not trained that you should never say 1 times 1 equals 2. You should never say 1 plus 1/2 equals 1. But it was very stubborn about certain things where instead of halfway through a proof saying, okay, we were trying to prove that it equaled 1, but it actually equaled 1.5, they would rather say, and 1.5 equals 1. So that they sound right, I guess? I don't know. It seems like there's got to be some fail-safe in there to have them not give some of the answers they give. Just, at least the 1 times 1 equals 2s and stuff like that. Or even their logical ability to contradict themselves. There was a lot of times they would say in the same answer, so-and-so is true, and therefore so-and-so is never true. You'd think that the language model would know, like, if you say an objective statement about numbers, that you shouldn't then say, that never happens. So, we could test it out a little bit. I have it open right here. And we might as well see 1 or 2 questions we've asked it before to see if it improves its answer at all or not. And let's start with asking it, tell me something interesting about a few numbers. And we'll start with, how about 1/2? They used to think that 1/2 was the... Well, let's start with 1, because sometimes they take facts about normal numbers and then try and apply them to other ones. So I'm wondering if it was the order I asked it that made certain things happen, which was after I'd asked it about 1 before, it realized after a bunch of wrong stuff, then it realized that 1 was the multiplicative identity element, I guess, because 1 doesn't change things under multiplication. Or maybe it realized 0 was the additive identity element, because then they kept saying other stuff was both of those. It said 1/2 was the additive and multiplicative identities, said 1/3 was also both of those, and it even clarified, like, these mean that when you add 1/3 to something, it doesn't change it. When you multiply something by 1/3, it doesn't change it. Same thing for 1/2, same thing for 2/3. And they also thought 2/3 was irrational. So let's see if they improve that at all. Tell me something interesting mathematically. I don't want cultural stuff right now. I want to hear its math skills. Okay, no, see, what? They updated this. Really? Really? 1 is the only number that is neither positive nor negative. You should at least, if your chat robot is going to say stuff like that, at least not have it answer, yes, I do, when you ask it, do you know basic arithmetic and simple facts about numbers, which I had asked it a day or two ago. Do you know this stuff? Yes. Tell me something about 1. It's neither positive nor negative. Let's see. And some of these are also just so vague. It's just like a student cheating their way through a paper. 1 can be used to describe the length of a segment or the size of an angle. You don't really usually see 1 describing the size of an angle. You sort of need a measurement, but sure. Okay, how about 1/2? I'm going to keep sticking mathematically in there. Okay. Okay, no. No, 1/2 is not used in the study of irrational numbers because it's a number that can't be expressed as a fraction. This is one of those things where it's just like, come on, 1/2 cannot be expressed as a fraction? Okay. What? 1/2 appears in equations as well as in E equals mc squared. Okay. I think they're thinking the squared was 1/2 somehow. Cool. How about 1/3? Okay, they're just going to say this about all of them, probably, that in geometry you can describe stuff with it. And nope, they also think 1/3 is irrational. 1/3 appears in the value for pi. What are they talking about? Okay, and this they're just mixing stuff up. It's maybe true, but some people try and put the golden ratio in their stuff, and some people use a thing called the rule of thirds. Maybe somewhat. Some artists have probably mixed those, but definitely not irrational. So now let's see what it thinks about negative numbers. So yeah, to all the folks saying, no, try it after the update. Well, this is it after the update. Someone said I should make a video or short about it. I did put some of these in a short. That was my last short, was some of the previous really bad answers I got. However, since a lot of people thought on that, oh, maybe some of these are because it was before the update on some of the answers. I will probably have to do another short at some point that's this is ChatGPT after the update, folks. Still pretty bad. And I also might make it into a whole episode on the main channel once I have like something interesting mathematically to discuss about AI, and then find the excuse to spend a few minutes throwing in some of the best ones of these. It was hard to explain them in a short. I wanted to put a bunch in, but I had to like rush through them. So yeah, I probably will make another short at some point that's about how even after the update it's still doing it. So let's see. Let's ask it about which numbers are the additive and multiplicative identities for whole numbers. And then I'm going to ask, because even though it would be the same for these other ones, I'm going to ask, since it seemed to get really thrown off by this, I'm going to ask, what about for negative numbers? What about for fractions? What about for irrational numbers? Because even though these are all just on the real number line, it seemed to before think a lot of stuff was weird types of identity element. Okay, so far so good. Okay, this part they fixed. Okay, they got better at knowing additive and multiplicative identities in the update. Okay, cool. They upgraded that part. Okay, let's see what else. What about additive and multiplicative inverses? Now, an additive inverse would be the negative of a number, and the multiplicative would be the reciprocal. Okay, so far so good. They're knowing about these type of elements. For some reason, they're really bad at facts about a given number, but when you ask them about a topic, they're getting a bit better. So let's see. Let's ask them about a few more random, slightly larger numbers. What's something interesting mathematically about 6? There's a lot they can say about 6. You know, I've given my rants about 6. More to come on that later. Okay, they got that so far. Should be a little more clear that these are just the proper divisors. They said it in that sentence, but not this one. And yep, it is a triangular number, but that's not just what it means. Consecutive whole numbers starting from 1. And it is the smallest number that's both, yeah, because of that. Highly composite, yep. It's even a superior highly composite, they could have said. And this is wrong. Whoa. 6 is a cornerstone of the decimal numeral system. No, what? Decimal's 10. And the number of units in a cube has nothing to do with the decimal numeral system, nor does the number of faces in a regular tetrahedron neither relates to 6 nor relates to the decimal numeral system. This one I like. 6 is related to modular arithmetic, even though it's not really specifically more than that much other stuff. But it is true that it has a lot of good patterns, which are part of why I like 6, because I like modular arithmetic. So this, I like their answer. That is good. So the others are not too bad. What about another slightly larger number? How about 24 number? Now, of course, they're just going to say hours in a day. Highly composite. Yep. They're good that they're naming those ones. We want to know about highly composites. They got them. They got them all. Cool. Okay, this is weird. They like saying this stuff about numbers that can be expressed as the sum of two squares in two different ways. I highly doubt this is true. I'd have to look into it for a moment, but I highly doubt that is true because they love saying stuff like that that's wrong. In fact, yeah, that doesn't even add up to it. 16 plus 9 is not 24, nor is 16 plus 16. So yeah, this is another example of one that's like a little bit off sounding, computer. You realize you're saying right here that 3 squared plus 4 squared equals 4 squared plus 4 squared. Okay, yeah, they got a lot of wrong stuff on this one too. Now, let's look at one more. We'll do 11. It's a prime number, it's true. It's one of... Okay, what? No. 11 is not single digit. There are 4 single digit prime numbers, but 11 is not one of those. Also, number theory and cryptography don't care about if they're single digit when written in the decimal system. They could have said, if we count in base 12, 11 is one of only 5 single digit prime numbers. Still wouldn't have anything to do with number theory or cryptography. I mean, the fact that it's prime does, but the fact that it's single digit in this base doesn't. 11, nope. Fibonacci sequence, the sum of the 7th and 8th terms. 5 plus 6. Those are not the 7th and 8th terms. Okay, now they just got using this copy-paste answer they said about 6. That was true about 6. A little less true about 11. I mean, you do use primes as a modulus, but not 11 in particular. 11 has a unique property in base 10, as well as in binary, where it is a rep unit, i.e. a number consisting of only ones. That is not true that's... if they mean the number 11 of a thing, in binary, that is not a rep unit. And if they mean the number 1, the number written like that, well, the number written like that in any base follows that rule. And so I'm assuming since the number written like that obviously would follow in every base, they mean the number 11 of a thing, which isn't that in binary. Okay, since that was so bad, we'll ask about 12 too. All right, I like that they know the highly composites. Abundant numbers, those are cool, yep. They really like this modular arithmetic answer. Okay, zodiac is not mathematical. These ones are a little more. And the dozen and the gross, yep. To those who don't know about the gross is actually an underrated number. It's 12 squared, 144. In base 12, it would be written 100. Very divisible. 12s come up a lot, so 12 squared has been useful. And the number 144 gets the nickname the gross. One of the worst nicknames to have if you were a number and got to pick your name. You would not pick that one. That number got ripped off even more than imaginary numbers. And speaking of 12s and nicknames, not only is 12 a dozen, and 12 squared gets another nickname, a gross, but 12 tens, 120, is known as the long hundred. At least it used to be, and at least in combo class it is, so... In addition to threeven, that's another term that we're trying to bring, but threeven is we're trying to bring forward. This one we're trying to bring back is long hundred. It's better than the normal hundred. The long hundred is as divisible as the normal 1,000. And someone asked, do I have ChatGPT Plus? I doubt it. This is the free version, but it says January 30th free version, which is when people claimed it upgraded. And, yep, there's lots of good comments and lots of good birds. And I'm going to pause on it briefly. I'll ask it about imaginary numbers because someone mentioned that. It didn't know about that. Oh, and of course, yeah, E. We have to ask it about E. So we must do E. And to whoever noted about the zodiac, I don't care if somebody follows the zodiac. People can follow whatever they want, but it doesn't have a mathematical basis. But it's okay to follow it because people can follow whatever they want to. But so I'm not saying I'm against it. I'm just saying it doesn't have a mathematical or scientific basis. And someone's saying, is there a reason I say 144 in base 12 would be 100? And yeah, because 100 kind of implies 100 of a thing. Like the number that we write as 100, that many of a thing. So it's very ambiguous since not enough people talk about different bases, how it should be said more often. Where if you're talking about a number in another base, whether 100 means what they would write as 100, then translated back to our base to be understandable to us, or whether it means 100, the number we know as 100, how they would write that. So it can sort of go either direction, and that's why sometimes although I'm not very strict on it or super clear, I sometimes will say 100 instead of 100 to be clear which one of those two I'm talking about. And people want to ask it about various stuff. I don't have time to ask about all this stuff. I'll ask it about I and maybe E, because it is E day, and then we might have to switch topics from this pretty soon. But I will do another stream on this for a bunch in my room sometime, because when I'm in my room, this is a good fun activity. So there will be some point before too long where I'll name another stream about testing whether the update is good at math or not. But we'll do one or two more for now. How about the number I? An error occurred. It crashed trying to think about a complex thing. No, not really, but where do I get my typey thing again? Okay, we'll just do a new chat if they let me. And we're going to say, can you tell me why today is E-Day? I haven't provided enough context for what that refers to. According to several sources, February 7th is known as E-Day. Do you know what that means? They're not aware. None of the sources they got fed included the articles about E-Day, apparently. Okay. E-Day relates to the number E. What can you tell me about that number? All right, we can see that they are using the way I said I don't like, which is the easy way out, where you say it is the base of the natural logarithm, and then you never define what the natural logarithm is. So they used exactly the technique that I said lazy teachers like to use. Okay, that wasn't very much. You've told me more about some other numbers. What else do you know mathematically about it? Okay, they're getting some good ones here. I mean, not perfect, but they're on the right track with most of these. Okay, so it knows more about E than it knew about 1. At least it doesn't think E is the only number that's neither positive nor negative. I'm going to ask it more about that particular one, because that was really interesting. Earlier you said that 1 is the only number that's neither positive nor negative, which is true. I'm going to try and make them think that they're doing good there. Can you please prove that? Oh, come on, robot. You're the one who told me that. Wait. This is why it's not true. It's because 0 is also a number that's neither positive nor negative. Oh man, when I read the first sentence, I thought they had fixed it. They didn't fix it. They just think that 0 is also that, which 0 is. But 1 is not. They think both of them are. So, okay, 0 and 1. Okay, 0 and 1. Can you demonstrate how that's true in the case with 1? If a number is less than 0, it's considered negative. In the case of 1, it can be demonstrated as follows. 1 is greater than 0, so 1 is positive. What? Look at this last sentence. Therefore, 1 is a positive number and is not considered to be neither positive nor negative. Okay, to all the people who said that they're making an update, the update is barely better. Okay, so they know about additive and multiplicative identities now, I guess, but they don't know about positive or negative numbers yet. So, maybe someday. All right, I think I'm going to take a pause on this for now. Thank you all for your suggestions. Maybe I'll come back to those when we do a longer stream about this in my room sometime. But for now, I'm going to wrap up the stream relatively soon. Feel free to leave any last thoughts or questions in the comments. And to everyone who hasn't after this stream, make sure, or who hasn't yet, after the stream, make sure to check out the episode that's linked in the description here on my main channel about pan-digital numbers and some weird paradoxical traits of them. So that's pretty awesome. Make sure to watch that. And stay tuned for some more fun stuff on here. I'll be filming the next couple days, which will mostly be for the next main channel episode, but will partially be for some shorts and bonus videos for here as well. And of course, you know, I like to do these live streams for fun. And you can, of course, also catch me on the Discord and subreddit, or if you're extra awesome, on the Patreon. And thank you all for all the really nice comments. Very nice. I always appreciate it. It makes me feel good to hear those things. Encouraging. I am, going to be continuing this mission no matter what, because I'm very dedicated, but the nice thoughts always help me go forward at the best rate possible. So, love you all. Hope you all are having a great day of your own. I'm going to wrap it up here. Hope you appreciate the number E. And if you've already seen that main channel episode of mine, then maybe just do some research about the number E when this stream ends, because maybe check out what some other websites have to say about it. And there's a lot of crazy places it pops up. It's going to be one of those things that will for sure pop up just random places in all sorts of future episodes. So, same thing with how our hyper 11s, our factorials, our triangular numbers, our three-even numbers, things like that just keep popping up because they're very fundamental concepts that happen to show up wherever. Well, know that the number E will do that as well. So thank you all so much for joining me. If you're extra helpful, check out that Patreon.